So this talk is about the implementation and optimization of multi-GPU discontinuous Galerkin solver, and in particular a solver for Maxwell equations. But I will not talk a lot about, I would say, Maxwell equation and result per se, but just focus on the HPC aspect of our development, because we are in front of a quite multidisciplinary audience. So it's maybe better to stick to, I would say, what we have in common, which is, of course, HPC. So the code we are developing is called GmshDG, which is multi-GPU, as the title say, discontinuous Galerkin solver, and it's based on GmSH, which is a code that we developed in the lab, which is a mesher. Currently, it only supports Maxwell equation, but we plan to extend it to other physics in the future. And also, we support both GPU vendors, so NVIDIA and AMD, which is lucky because, of course, about LUMI, we need to support AMD. And let's say it's still in very early development. We are not at a stage where, I mean, for full production run, it's completely ready. And our goal with this solver is really to solve large problem. This is why we focus on GPU developments. So we want to solve a problem with a lot of unknowns, so billions of degrees of freedom. Short introduction regarding the method, even if it's not so important to understand the rest. So what is discontinuous Galerkin? Well, it's a method, okay, a numerical technique for solving partial differential equations, and it combines finite elements and finite volumes method features. And we represent the solution as basis function, okay, defined on individual elements that I call T, because in our case we use tetrahedrons, okay, but we do not enforce continuity of the solution across boundaries, okay? So if you are in a continuous case, well, the value at the boundaries are the same, and in that case, in discontinuous Galerkin, we don't enforce the continuity of the solution. So, as I said, what we do is represent in this case, the electric field as this sum with the coefficient there. This is what we are interested in, and a multiplication by basis function located in on the nodes. Okay, and if you apply dg to the Maxwell equation, in this case for the electric field, you end up with this. And the important part to understand, I would say, what we talk about, what we talk in the next part of this talk, is that we have a surface contribution and a volume contribution. And the consequence of this is that we have a surface contribution, meaning that we have exchange across the boundaries. And as I told you before, we don't have unique values at the boundary, so we need to kind of emulate something so that the value at the interface are uniquely defined, okay, to ensure unique interface value, stability, and also conservation. And in DG, what we use is called numerical flux, okay, in order to kind of emulate continuity at the interface. And when we compute that, one of the operator we use is the jump operator, which becomes important in case of the multi-GPU solver, as we will see, where we need to have the value of the field at the boundaries, okay, on one element, and when we have two elements, okay, we have values that are different at these elements, so we have to compute this jump operator, and so we need at some point to exchange data between the elements. So what we end up with, okay, so our solver looks a little bit like this. We have the two paths, the volume path and the surface path. The volume path is quite short, okay, we just have to apply a curl operation. So it's quite short. The surface path is a bit longer, okay, in particular where you are in the case where we are on the multi-GPU, okay, we have to compute the jumps. What I call the local jumps is the jumps that are within the same domain, okay, on the same GPUs. However, for the jumps that we compute across the boundaries of different domains, well, we have to exchange some data for the computation of these jumps, then we can compute them, and then we have a step that is called flux, computing the flux, and then the flux lifting, which basically take these flux that are on the surface and bring them to the volume, and then you combine the two and you get a solution, okay? So we use Gmesh for the creation of the mesh, and Metis as the graph partitioner for the multi-GPU case. Okay. Regarding the implementation, okay, we made the choice to start from scratch. Don't use linear algebra libraries. So this was a choice made at the beginning of the development, not by me actually, but by the guy that started the project. So I kept using, I would say, our custom kernels. And in terms of, I would say, portability, this is very simple. We don't do something that is particularly complex. We just use macros, okay? So in the case of, for example, a heap malloc or a CUDA malloc, we just redefine it as GPU malloc, and it ensures portability. And most of the GPU kernels, I mean, there is a few differences, but most of the time they are exactly the same because the kernel language is the same. At some point, we started using Cocos to see if we can achieve portability on both the GPU and the CPU with exactly the same code. Unfortunately, while the performance on GPU was quite good, close to the CUDA implementation, so native implementation, we had a lot of problem with vectorization on CPU, so the performance on CPU was pretty poor. So this was a test, and we decided that in the end, well, maybe we will not continue with this option. Okay, so if we look at our goal, okay, what we want is good single GPU performance, of course, and in terms of solving large problems, okay, tens of billions of DOF, well, we want also that our multi-GPU implementation present a good performance. So that will be the two parts of this talk. So if we focus on single GPU performance, okay, so this is a comparison of our solver on CPU on a full compute node of our tier 1, so Lucia, which has exactly the same CPU as the one on LUMI, so you can expect exactly the same performance on LUMI. Okay, and you have the throughput in terms of gigadov per seconds, and then you have the same throughput for different GPUs, so the NVIDIA A100 for Lucia, and then the MI250X of LUMI, and the H100 of Marinostrom 5. So, and you also have the speed up there relative to the CPU. And of course, what we want is that if we consider a full CPU node, okay, we have about, and we go to one single GPU, we have about 4 times the memory bandwidth and also 4 times the compute power. So we expect something around 4 in terms of speed up. And depending on the order, okay, the number of nodes we apply on each tetrahedron, well, we don't exactly get this speed up except for the very high order, so 4 and 5, and then 6 we have a drop, and I will explain why later. Regarding LUMI, I was wondering how to present this because we have 2 GCDs per module, so I chose to present the result per module because in terms of price they are about the same. Okay, if we pay the compute time, it's 50 cents for one full CPU node and 50 cents for one GPU module. So in terms of comparison, if we want to see if we are efficient, well, we need to compare at that level. However, you can see that on a single A100, we get almost the same performance as on 2 GCD on LUMI, so it means that we get lower performance on LUMI in terms of comparison single GPU to a GCD. And also, we don't get as much as a speed up, I would say, on an H100 compared to the A100. So that kind of result were disappointing, and we want to understand why. Well, in terms of why it doesn't, I would say the speed up we have between the CPU and the GPU depending on the order varies. Well, because we have different behavior if you look at what our kernel can achieve at different order. Because we have few kernels there, okay, which are the computation of the flux, the jumps, and the time integration that are always compute bound, okay. However, going from order 2 to order 5, well, or two kernels there, so the curl and the lifting, move from being mostly a memory bound to a compute bound region. And the reason for that is that most of the, I would say, operation we do in the curl and lifting kernel is basically a matrix multiplication, small matrix multiplications, but matrix multiplication nonetheless. And so the inner loop inside of our kernel is longer, I would say, when we increase the order, and so we have more flops, I would say, done inside of the kernel, more data reuse, and so we move from the memory bound region to the compute bound region. Now, if we look on LUMI, well, there we have a problem. We are fine for kind of fine for memory bound kernels. It's almost the same value, but we can see that we don't achieve good performance on the curl and lifting kernel. Okay, we are way below the peak performance of LUMI, and so this is why in terms of GPU A100 to 1 GCD of MI 250X, well, we had such a poor, I would say, speed up compared to what we can expect from the peak performance of LUMI. And actually we had kind of a similar problem on H100, okay? Except that we can achieve better performance, okay? And it is kind of interesting to compare this NVIDIA H100 compared to LUMI, is because there seems to be custom card, okay, with about the same memory bandwidth as GPU on LUMI. This is the one from Nostrum 5. Okay, so we are comparing exactly the same memory bandwidth, and in terms of peak compute performance, okay, on LUMI we are at 33 teraflops per GCD, 26 teraflops per GPU for H100. So in terms of performance, these cards are quite similar, and we achieve better performance on an H100 than what we have on LUMI. So depending on the hardware vendor, we don't see exactly the same behavior. So as I said, these kernels are mostly matrix multiplication. I will skip that slide for the sake of time and go faster. And the real problem we have actually is not that we are not really compute bound, we are L1 bound, okay? And this is one of the main problem, I would say, is a choice of AMD at some point. To provide a very small L1 cache, okay? If you compare A100 and H100, okay, you have more than close to 200 kilobytes of L1 cache, while on LUMI you only have 16 kilobytes of L1 cache. And the bandwidth is also lower, and also we observe an arithmetic intensity that is slightly lower on LUMI. So, and you can see the effect of the L1 cache, we say size, on the cache hit. It's way lower on LUMI, and this is actually what limits our performance. So what we want to do in the future, but it necessitates to restructure a bit of the code as well as the kernel, is try to use the LDS on LUMI, okay, where we have way more bandwidth, and try to achieve exactly the same arithmetic intensity we have on NVIDIA, and hopefully we can get this number in the end, which would be a better use of of LUMI. Okay, we skip this. It's about power efficiency. I can just tell you that the GPU is more power efficient than the CPU. Okay, so regarding multi-GPU, we don't have a lot of data to actually exchange during our computation, and in a sense the implementation is relatively simple, and we use something that is very common in HPC, okay? So we have a few values that may not be stored continuously, but anyway, we want to send them. So what we do is that we pack this data, just send it, receive it, and at the end, we can compute our jumps from the field we receive from the neighbor. Okay, and our first implementation where we choose to be very naive, okay, just do MPI send and receive, and try that on our tier 1 Lucien, well, it didn't lead to good performance, okay. Up to 32 GPUs, okay, we have some improvement, but the parallel efficiency is very low, and after that, well, it was even worse. We didn't get any improvement in the throughput. So what we decided to do is to switch to, of course, asynchronous communication or using MPI send and MPI receive. Well, it leads to a good improvement, but it was not so great, okay? If you look at 64 GPUs, we are at 60% parallel efficiency, so our goal to, I would say, use billions of DOF on hundreds of GPUs is far from being reached. So what is the limit on our scalability? Well, one thing is that as we increase the number of GPUs, we have less work per GPUs and we don't manage to saturate them, but okay, we can just use a larger problem size and the problem is solved. But we still have a problem of communication to computation ratio that increased as we increase the number of GPUs. So what we want to do is to hide this communication. And to do that, well, we can exploit the fact that we have an extra dimension, okay? When you are on CPU, you have to do the computation and the communication, okay? But you have two dimensions. The NIC can do part of the work, but you are on the GPU, well, you can do computation on the GPU, as well as doing some work on the CPU and taking care of the communication. So the idea is to move part of our computation on the GPU on a second GPU stream, okay, and manage them by overlapping the execution with the kernel. Because I would say these are quite short and should not impact too much the kernel, okay? Because of course we are sharing resource on the GPU, but we don't expect these parts of our calculation or at least communication to impact too much the GPU kernel. So the idea is, say, create a computation stream and a communication stream. For good performance, we had to put the communication stream as high priority. Okay, this is saying to the GPU, we want this to be the first thing you consider when you choose what to do. And for the coordination between the two streams as well as the CPU in terms of MPI communication, where we use HIP or CUDA events, okay? So we submit everything so that we don't pay the price of launching kernels, so we launch everything at once, and then we coordinate this different stream as well as the CPU for the MPI call using events. And this is what it looks like, okay, if you take a trace. Okay, so you have the main calculation there, you have the kernel executing, and there you have the packing kernels and unpacking and jump computation kernels. In red you have actual communication going on the GPU, and all this activity there is all the events, synchronization, launching the kernels, calling MPI. Well, so we do all of that. And so the communication phase completely overlap in terms of execution with the kernel. So as long as the kernel is run for long enough, well, we are safe. We should be able to hide communication completely. And indeed, if we go again on Lucia, well, we get 80% parallel efficiency for this problem size for 64 GPUs. But 64 GPUs, this is the limit of the number of GPUs we can use on our tier 1, so we want to go further. And if we want to compare that to a similar GPU, so another system with A100, well, we go on Leonardo. And on Leonardo, we can confirm that we are quite good up to 100 GPUs, but after that, well, it starts clearly to drop, and this is because we cannot hide the communication anymore with our curl kernel. Also note that the Leonardo GPUs have a different power limit, so they were faster actually than the one of Lucia, so of course the curl kernel was executing faster than what we were doing on Lucia. I had to, in some cases of this measurement, I had to do them multiple times because the Leonardo network is not always stable when you go from one cell to another in the network. And you have to make sure that you have nodes close together to get reliable result, because I've seen huge variation, which can be mitigated by some environment variables, but it was not a good experience in some cases. Okay. What we can do to kind of improve and go further is change the time integration from Leapfrog to RK4, where we have more time, I would say, to hide the communication, because we have two curl kernels that will execute at the same time. And then indeed, yes, we can go to almost good performance up to 256 GPUs, but after that, we cannot. Okay. And this result actually can be reproduced on LUMI, and it's even better in some cases. You can see that at the beginning, I mean, the scaling efficiency on LUMI was pretty good, and then we see exactly the same effect. We cannot hide the communication as well, and we see a drop in performance, which can be improved by switching to another time integration and having more time to hide your communication. But, well, we have been able to go up to 1024 GPUs to a good parallel efficiency. So we are pretty happy at that point. But we still have some improvement to do, because we have a problem of memory consumption of rank 0, which leads us that is the maximum size we can use at the moment. So we need to improve the code in order to go further, but this is in work in progress. Okay, so I did some weak scaling, of course, to confirm, but it's not that important. And in terms of what we want to do in the future, well, we still have a lot of latency that appears due to the event synchronization on the CPU as well on the GPU. So what we want to do is try to keep as much as possible on the GPU, which means the communication, we want to try to do it on the GPU as well. So what we want to try is some feature of CREMPIC with stream-triggered and GPU-triggered communication. Last time I tried, there is something in the documentation that is not actually in the library. I didn't find the symbol, and it was not in the header file, so I didn't manage to, I would say, do what I wanted to do. What was presented in the documentation was not on the system. I hope the next update will fix that. And for NVIDIA, at least, I want to try using NVSHMEM. I don't know about RockSHMEM, because it doesn't seem to be actively developed by AMD at the moment, so we have to see. But at least try these two approaches so that we have something that works on NVIDIA and AMD system at the moment. So, and all I have to do is thank you for your attention, and sorry to be so fast to try to